Hello, and welcome to today's talk. I'm Martin Stanicle. I'm president of the List, and it's my great pleasure to say hello to see nice to see some people at lunchtime, especially in an unusual setting for our events. I think we've had many chapels in the past. It's very splendid. We're looking forward very much to today's talk. We're going to hand over to Alex Taylor, who's going to introduce today's meeting. Thank
you. Today's speaker is Professor Stephen Moss. I'll just read this because I'm not over a bit, so it's quite a hefty one. Professor Stephen Moss became director of NERC's National Centre for Atmospheric Science back in 2005. His experiences in atmospheric dynamics, with applications in boundary layer and mesoscale meteorology, and also in chemical transport. Much of his research involves atmospheric observations combined with computational modeling. Professor Moss received BSc in physics and PhD in applied mathematics from the University of Leeds. From 1996, he was head of the School of Environment, and following the merger with Earth Sciences in 2003, he became head of the newly formed School of Earth and Environment at Leeds University. He is a fellow of the Royal Meteorological Society and serves as a member at the Institute for Climate and Atmospheric Science and Atmospheric Cloud Dynamics.
Thank you, Alex, and welcome to all of you. Welcome to our building to NCAS, the National Centre for Atmospheric Science. Yes, it is quite a splendid meeting room.
I think the mic's on. It does pick up everything.
Yeah. Can everybody hear okay? Yeah, good. Yeah, so welcome to our institute. We are one of the 6 research centres of the Natural Environment Research Council. But NERC uses a different mechanism for each of its centres. One's like the British Antarctic Survey, they just own. In our case, NCAS, they place a contract. It happens to be with the University of Leeds. But then we contract the work all over the country. So we have 12 partner institutes around the country, all doing atmospheric science. This talk there's a certain element of sort of looking back, and it's a personal perspective, and it's over the last few years. I think perhaps you get to a stage in your career when you look back and you not just think about what you've achieved, but also how the discipline has changed, and not just genuinely changed, but it's changed because you have a very different perspective, and things that you think, how could I not know that when I was in my 20s? And so we'll come up with some of those. Now, when we did this before, it took a lot. Oh, that's it. We'll just do that. Yeah. So a bit about. I don't have a pointer. It's a indication of age, maybe. I for years in this room, and I lectured in here. I just don't like it. You know what? I hate sort of pointing on screen. I like a proper pointer, you know. So yeah, we'll use the bamboo again. Yeah. So atmospheric science, and I need to explain a bit about what it is. It's sort of obvious to do with the atmosphere, but why is it a scientific discipline? And there's a strong argument that it really got going only in 1950, and I'll explain why. So up to 1950, there was the atmosphere was the subject of sort of myths and legends, and a relatively small number of what you might these days called gentlemen scientists. And something happened in 1950, which was the invention of digital computing, which completely transformed this subject. And in a very real sense, we've spent 75 years since 1950 building on that and supporting it. I'll explain that. But the reason I got sort of more interested in this was you could think of what happened in 1950 as a revolution in atmospheric science, but we're in a very real sense in the middle of the second revolution in atmospheric science. And you might think, well, everybody can say that. It's to do with artificial intelligence. But actually, in a very real sense, atmospheric science has been impacted even more than some other disciplines. So I'll explain why that is. So just a little bit, why does anybody study the atmosphere? I would say we're regarded by NERC as one of the sub-disciplines of environmental science. We have a sort of disadvantage because nobody can see what is the thing that we study, except clouds. But the atmosphere is a key part of the environment that we live in, and it protects us from the harmful radiation. There wouldn't be any life on Earth without the atmosphere. Over the past, particularly over the past 30 years, people have become more and more aware of the relationship between society, or more broadly, the future of humanity and the atmosphere and the future of the planet. So that sort of drives a lot of why we study the atmosphere. And then the question, so what does this thing look like? And there's this big problem. You can't really take a picture of the atmosphere. You can. This is one. This is from the space shuttle. You can see the curvature of the Earth. You can get a bit of idea of the scale. And this is the atmosphere. You can really see it's very thin, extremely thin layer over the around the Earth, and as it's within it, it's extremely layered itself. Yes, you can see it from space. I was quite pleased with this picture. This is my best attempt to take a picture of the atmosphere actually from the ground. And you can actually see the same thing. You're looking up to about 10 kilometers here in the far distance. So you can really see something. And these clouds are they're not cirrus clouds that you normally see when you look at outside. They're at 90 kilometers. So that really is the top of the atmosphere pretty much. So quite recently we updated our research centre strategy, and I was reading it back in the context of what I'm saying today. Yeah, everybody can say this, can't you? Yes, we're a global leader, and we're going to in the research and innovate and address many of the important environmental challenges, and we want to be produce high quality science that everybody trusts and so on. It doesn't actually give a sense that we're on the verge of something rather dramatic. Let's start by just looking back at the beginnings of the subject, and then to set some sort of context. I won't say this is the very beginning of atmospheric science, but it's something that caused a lot of amusement, and actually recently some controversy. So this guy, who is not particularly known for his sort of consensual way of governing, he forbade all kinds of sorcery, such as forecasting the weather. I remember it being first announced, and it was actually in a Royal Meteorological Society. Somebody had found this and pointing this out very pointedly to the Met Office. But forecasting the weather was forbidden. Recently, there's been, when I started quoting this, it sparked this controversy, and lots of historians piled in, and a big arguments that started with the Met Office. It turns out that the document that quotes this is actually in the National Meteorological Library, which the Met Office look after. So, I don't think they really resolved this. Some of them saying, no, he wouldn't possibly have done that, not because he was against forbidding things or chopping their heads off if people disagreed or whatever, because it was there was things which you could call forecasting the weather going on in 1500s. But anyway, never mind. It certainly wasn't science. So you've got to go to about 1600, and then there's the beginnings of things that you could call science. So the idea of temperature and the idea of rudimentary thermometers coming at about 1600, understanding of the gases would come mid 1600s. Boyle, Torricelli, the idea of atmospheric pressure or the pressure of the gas. Although thermometers existed for a while, it wasn't until about 1750 that people started to be able to describe a temperature scale, so you could actually quantify temperature. And the sky Celsius, and there was another one, it was picture I didn't put on there, it happened to be called Fahrenheit. It was about the same time that atmospheric electricity was beginning to be understood, and this was the beginning of people trying to understand this new phenomenon of electricity. And Franklin nearly killed himself a number of times trying to tap into the lightning. This was that amusing. Turned out that the concept of the greenhouse effect, I should say, don't know, most people got some idea of the greenhouse effect. It's basically some of the gases in the atmosphere are not very transparent to the radiation that that's reflected or transmitted from the Earth's surface. It traps the heat. That's how greenhouses work as well. It's there, it's the glass. And we all know about this carbon dioxide, but there's other trace gases that are even stronger green. That concept, in the context of carbon dioxide, was discovered at pretty much the same time by two people who there's no evidence they knew of each other's work or ever. One of them Eunice Sparks, the other one John Teddy. As the pictures. Who do you think got the credit? So it's still in the last 20 years that people have realised what Eunice Sparks did. Yeah, that's the sort of typical, I think, about any scientific discipline. But I'm afraid when I gave a short version of this talk, and then I was challenged afterwards, I said, yeah, but you need to improve this. You need to quote the work of more women. The truth is, sadly, until about 1950, there aren't any often used photos. Been much better since then, I have to say, and we'll see some examples of that. But yeah, I mean, I'm afraid this particular discipline was probably certainly worse than, say, chemistry. Yeah, move on. People were beginning to understand how the atmosphere moved and the structure of it and different climate zones around the Earth by sort of mid-1850s, and beginning to turn that into some sort of arm-waving form of weather forecasting by the 1860s with Admiral Fitzroy, who was the captain of Darwin's ship when he went around the world. End of the 1800s, this guy Arrhenius was the first person who went from the concept of greenhouse gases and said the world will warm if we put more greenhouse gases in the atmosphere, and actually came up with a number. Remarkably, the number is extremely close to that we use today, based on enormous supercomputers. So he was quite influential. By the early 1900s, people were beginning to write down equations and regard the atmosphere or the motion of the atmosphere as a branch of fluid dynamics. Jakob Bjørnnes was very influential in Norway, not only in writing down the equations, but developing what these days are called the Norwegian model of cyclones. So what we understand about Atlantic depressions of cyclones largely comes from the 1920s, and it's a group of Norwegians in Bergen. Bjørnnes was the third in a dynasty of Bjørnnes's. Anton, born about 1820, something of hydrodynamicists. Wilhelm was the first person who wrote down the equations, but then Jakob turned it into something tailored for practical use in the atmosphere. One of the problems in atmospheric science is, until recently, how do you observe it? You can have a thermometer, you can go outside, you can look up at the clouds, but to get real data about most of the atmosphere up to the 10 kilometers or so is difficult. Certainly was in the early days. So the invention of weather balloons, or the instrument that goes on with the radio songs, was a very significant thing by Benjamin Robert Bureau. He was obviously extremely secretive chap, because I searched and searched for a photo of him, and there just doesn't seem to be one at all. I managed to find this, which was a group of sort of radio engineers in the 1920s. I'm pretty sure the guy on the back row at the end, which is probably typical of him, is this man. It says M. Bureau, but I'm pretty sure that's Mr. Bureau, not because it is Robert Bureau. So that was very important, because then you could start to measure the atmosphere going up, all the way up through the atmosphere to the 10 kilometers. It took till 1938 was when the first actual measurement evidence of global warming came along. Guy Callendar. Now we start to link to the more modern things. I'm going to come back and talk about what was going on here. Some people, Louis Fry Richardson, worked for the Met Office at times, and attempted to use these equations that have been developed and to actually compute a weather forecast using that. So we'll come back to that in a minute. It didn't really work, but again, we'll discuss that. The first successful numerical weather forecast was done in 1950, and this is relevant talking about. I'll just briefly mention a few other things. This measuring the time series of carbon dioxide year on year, going up and up and up. It's been done in the Hawaii Islands since 1958. Charles Keeling ran that, and then his son took over. Looking down on the atmosphere rather than sending something up was very important. Weather satellites started to come along in the 1960s. Doesn't solve all the problems, although you can look down from space. The problem we've got with satellites is they don't see the bit of the atmosphere that matters most close to the surface, because there's other things in the way. Clouds, obviously, but also the rest of the atmosphere. So massive transformation, but not the answer to all questions. Obviously, this is something to do with computing the weather, but that over the next 20 years or so was also extended into computing the climate, and very influential work by Manabe and Weatherall. Late 1960s was the first computational climate prediction. So the things that have happened since then, acid rain was big in the news in the sort of late 1970s, 80s. You don't hear so much about it now, but largely because in sort of our part of the world, we've cleaned up the atmosphere somewhat, but it's not such a big problem. The ozone hole is still a big problem. The Montreal Protocol sort of controls it, but there's still issues about that. And just as an amusing aside, we can go back to the previous slide. This guy, he certainly isn't a major figure in atmospheric science, but I came across him. I thought it was amusing. Thomas Nigler was the person who invented CFCs that caused the ozone hole. Turns out he was also the person who invented lead in petrol. So his contribution to the environment is great. He spent 2 years recovering from lead poisoning because he tried to demonstrate that there was no harmful effect for his lead in petrol. Okay, so let's move on. Right, let's now talk about this guy, Richardson. Oh, by the way, it's discovered as a distant relative of, I think one or two of you here will probably know the name Julian Hunt, a well-known mathematician from Cambridge. Lewis Richardson is a distant relative of his, and because Julian Hunt for a while was chief executive of the Met Office, so there's obviously a family thing going on there. So Richardson joined the Met Office and worked at the Eskdale-Muir Observatory, which is not terribly far from here, near the Scottish borders, in 1913. But he was in those days, the Met Office belonged to the, well, whatever it was called, the Ministry of War, I suppose it was called then. Richardson was a conscientious objector during World War I, so he left the Met Office and went. He drove ambulances in Belgium and France during World War I, but kept on working on his science while he was doing this, and developed a method, in principle, for taking the equations that describe the motion of the atmosphere and computing a weather forecast. And in fact, he wrote a first draft of his book, which eventually was published in 1922, and he sent it back from the front line wherever he was, and it got lost. And it was years later that it was rediscovered and eventually published. So when he got back to England, they actually put this into practice, and they described the atmosphere on a grid of points over the UK and the surrounding area, with 12,000 grid points, which is an awful lot actually, and 5 levels globally. But only computed the answer at 2 of these grid points. The question is, how did he do it? So I assumed for a long time he would have used one of these mechanical calculating machines. I'm sure there's people here who have actually seen them or even had it. Yes, one of those, Bun's Vigo thing. Turns out he didn't. He didn't. This is how he did it. Slide room and not tape, I'll pass them round. So that's the basis of computing in those days. I'm really surprised he didn't use the calculating machine. Anyway, he didn't. So what happened with this weather forecast? Well, it was a disaster. It just completely failed. It didn't work at all. We now know that it was a combination of things. It was the data he used to start the forecast was hopelessly inadequate. So weren't the measurements, and also in what we today call computational science, his numerical algorithm was on what we would call unstable these days, and we use computers who would say the model blew up. So none of these things, of course, were known because we didn't have access to the computational facility. But this is really impressive. So he was very sort of forward-looking. I was thinking about, so how would you actually turn this into a global weather forecast? And this is from his book. This artist, Stephen Conlon, has produced a painting to try to describe what Richardson describes in his book. And it's this sort of spherical building. This is a cutaway where the whole of the earth is divided into segments on a grid. And there are people in offices all the way around it who are working away on the computing the bits of the weather right in their particular part of the earth. We'll come back and just think about this in a few minutes though. But you can see also this tower in the middle. This is the guy in charge giving orders from the top of this tower and controlling everything. And ultimately, you end up with weather forecasts on a grid like this. So, of course, this was never actually put into practice. Here's some of the people in these offices doing the computation. In charge. Some of you will remember. Do you remember department stores that didn't have tills? That there was one office somewhere, and they sent everything in these pneumatic tubes. So all of the data would be passed around the building under those tubes. Almost everything you see here has an analog in a modern computer, except this needs book. Oh, that's this guy. He's currently retired now, but he's done a lot of the illustrations for the National Trust. Right. So Richardson was very forward-looking, but it didn't work. So they had to wait a while, and then during World War II, there was a big incentive to accelerate the invention of digital computers. And the first computer was this ENIAC, the electronic numerical integrator and computer. It didn't really come along in time to influence the war effort, but it was more or less finished by the end. So it first ran in 1945 for military applications, and after the war, people started to think, so what could we use it for? And really, the first civilian application was computing the weather. And that set a trend, actually, because certainly until the last 10 or 15 years, in a very real sense, weather forecasting has driven the growth of supercomputers. It was always the application that the supercomputers had to be able to deal with. So this computer, this first computer, this was before you mostly know, I think, that modern computer processors are just a huge number of diodes, electronic switches, but there were no diodes then. So they were, instead, they used these thermionic valves. So I thought I'd bring one along. To have a look at, and so there are 8,000 of these in the ENIAC. is about. The problem is they're like light bulbs, you see, and they don't last very long like light bulbs. So if you had 8,000 light bulbs, how frequently would one fail? Quite frequently is the answer. So this thing had 8,000 of those bulbs, 10,000 capacitors, 6,000 other switches. It was enormous. 49-foot tall panels, and there was 140 kilowatts of power. And it was programmed. Programming was mainly about feeding in cards, but also you had to wire the computer to do it. And in these early days, the people who did that were called computers. So it was only later that the term computer came to mean only the hardware, if you like. There's another picture of it, and all of the computers were winning. I don't know whether that might have been partly influenced by the war effort, and it was like Bletchley Park and the code breaking, a high proportion of women as well. So in terms of speed, we measured the speed of computers in floating point operations per second, and it did 500 of these. That was its speed. So just for comparison, I even bought, especially for this talk, a computer called a Raspberry Pi Zero. It cost me £9 something. And this is 250 megaflops, or 250 million flops. So this is 500,000 ENIACs. To give some idea. Your smartphone is more like 5 million megaflops. So that's about 10 to the power of 10 ENIACs. And the latest supercomputers are something like 10 to the power of 18 ENIACs, just for comparison. So you can see, actually, in principle, we can compute things that were quite difficult in the past.
Sure.
So, what happened? So, after the war was over, these guys, Charlie, Piotr, von Neumann, and some others, attempted a weather forecast on this ENIAC computer over a very small grid. This is their grid with dots, and they basically only North America, and it took 24 hours of computer time to produce a 24-hour forecast. So they could just about keep up with the weather. Only they couldn't, because remember, those thermionic valves don't last very long. So in real time, it took 33 days. The rest of the time was replacing valves, you see. However, at the end of all of this, out came the results, and it was convincing. Essentially, what they demonstrated is, in principle, you could compute the weather. In terms of it being a young subject as well, so that you tend to think, or at least I did, when I came into this subject, something that had gone on forever and ever. One of the first realizations that wasn't the case was my very first conference as a young PhD student. Charlie was there. So I link back to the birth of modern atmospheric science. So what happened? Well, we don't have an objective analysis of what their results. I mean, there's pictures in the paper. It was reproduced by somebody called Peter Lynch at the Irish Met Service much more recently, and actually programmed this on an iPhone as well. But they did some real sort of objective analysis of these forecasts, and they have real skill. But that's the point. So this was the starting point, and that's 24 hours later from what actually happened going from that to that. It doesn't really matter what it's showing. And that's what they computed. It's not, by modern standards, very good, but there's a small amount of statistical skill in that. The point is they've shown that it could be done. So that was the revolution. Suddenly, it became possible to compute the weather. And within a small number of years after that, the value, societal and economic value of weather forecasts was absolutely obvious. It became something that you couldn't imagine not having. And this motivated an explosion of science. So where does the science come from? It's not that everybody's running these computer programs on ENIACs. It's that to build ever better forecasting models to run on the computer needs a huge amount of science, ranging all the way from how to measure the atmosphere and lots of technological measurements, how to represent those measurements in computational models, how to understand what's coming out of the models, and so on. So that sparked essentially the 75 years of atmospheric science. And anybody these days who writes advanced applications is trying to get funding in atmospheric science. Somewhere at the end, they'll make some reference that this is the impact that this will have, and it will include this aspect of a model or something like that. So that was the revolution. So that's basically what we've been doing for 75 years. And these days it's much more sophisticated. So I'm not going to go into lots of detail here, but essentially you cover the Earth with a computational mesh. Note the similarity between this and Richardson's fantastic forecast factory. The only thing is the connections in here are going on inside the Raspberry Pi or the ENIAC, not with people running around. Huge amount of science, what we call process models going into that. These are the equations and lots of things that have to be represented that even in the biggest computers we can't represent because they can't be resolved like individual clouds and so on. So it's not the purpose of this talk to talk about the details of what's gone on in those 75 years. But as I say, in a very real sense, atmospheric science has been driven by improving these weather forecasts. That's like tomorrow's weather. And I said a little earlier, it took 15 years maybe for that idea to be extended into computing not just the weather but the climate. So starting to talk about what will happen in 10 years' time or 100 years' time and so on. So computing the future climate. Things like long-range weather forecasts, what will it be like next month? Being subject to huge amounts of research, incredibly difficult problem actually, that's sort of on the margins of things like chaos theory. You can't predict next month's weather because the system is chaotic. I think it's gone beyond that to other aspects of the atmosphere, and especially the dispersion of pollutants and the link to health and so on. So you emit something from a factory or something, where does it go? And those are models that predict that are very similar to the weather forecasting model. So that's what we've been doing. Very quickly, it wasn't just that a small group of people were running a big computer program. The subject came into being not just because some random group of people were contributing to it, but because there were organized efforts to organize atmospheric science as a subject, and particularly in the United States. So our opposite number in the US, it's the national, almost the same name. They're the National Centre for Atmospheric Research. They're older than we are. They came about in the late 1950s because some quite forward-looking people, who included Charlie and von Neumann and other people like Teller, who was big in the development of the atomic bomb and things. They recognized that atmospheric science was this big new subject and made a case for a new research institute, which practically became NCAR. As if you read what they said, this really is very forward-looking because it all applies today. We need to mount an attack on the fundamental atmospheric problems on a scale commensurate with their global nature and importance. But such an attack requires facilities and technological assistance beyond those that can possibly be made at individual universities. How often do we quote this in this building? Because we coordinate lots of things across lots of universities. The problems are such that they require the best talents from various disciplines to be applied to them in a coordinated fashion. And the Institute offers the possibility of preserving the natural alliance of research and education without unbalancing university programs. All of that's absolutely true today. And they wrote lots of things which is very accurate today about what would be needed. If you underestimate, they thought 108 research scientists were going to be needed. I think NCAR's about 800 or something these days. All of this, pretty much, you would say is equally applicable today. There's one thing I put it for amusement. Remember, this is written in the 1950s. And they were concerned that by setting up this institute, it would suck all the best people out from across the US and would leave other areas deficient. So they were addressing that and said that since the number of preeminent men in any field is small, the recruitment of first quality scientists was proceeded with careful regard for excellence. So that's the one thing in this that really dates it. And of course, NCAR and NCAS are much more balanced these days. We got there eventually in the UK as well. It took us till 2000. This was our birth, and we don't have anything grand like the NCAR Blue Book. We have some scruffy sort of NERC council minutes or something. But yeah, the reasons why NCAS exists are pretty much the same one. Right. So I'm going to move on a little bit and talk now about what has been the effect of all the science we've done for 75 years. And essentially, it's that the accuracy of weather forecasts has just increased and increased and increased. We'll take a moment to explain this plot. What we're looking at, these are years from, this one goes back to 1981, we could go back to 1960, almost to the present day. And this, for example, take the green line, that's a 5-day weather forecast. And this is saying that in 1980, it was 70% accurate. And that today, it's 90% accurate. And year by year, the forecasts get more accurate. And if you look at it, if you want a shorter range forecast, it's more accurate. And if you want a very long range forecast, back in 1980, a 10-day forecast was 20% accurate. Using that's useless. These days, it's around 50% accurate. So that's beginning to get sort of useful. And there's this rule of thumb, which is applied, we can't really read it off the ground, but the accuracy of weather forecasts increases by 1 day for every 10 years. In other words, 10 years from now, you'll be able to get a forecast with a similar accuracy, but 1 day longer than you can today. And this has been remarkable, and it's persisted for over the 75 years. I won't talk about this. This is the same. This is just another measure. It's the forecasting the tracks of hurricanes. And what was sort of in the 1960s, you could sort of do 500 miles, and you're now talking about 100 miles or so. So huge advances. So why? How has all this science led to these better weather forecasts? Well, here's some of the reasons. And you would like to think that better understanding of the atmosphere and its process is the most important thing. All these people working for 75 years. Better representation of these processes in the computational models. These are the components of the models. Yeah, that's very important. Better computational science, in other words, better algorithms for turning the model into something that runs on a computer. Yeah, that's still important. Better observations to drive the models. More observations. Yeah, that's also important. But very sadly, I have to say, as someone who's worked in this field for 40 years, the biggest single contribution is bigger computers. So that's a bit sad, really. But it's not to say the other things aren't important. They are very important. So that's why we have this ever-increasing accuracy. So, what next? We've come from 1950 with the ENIAC experiments, and we've got this ongoing process of ever-increasing accuracy. Where does this go next? And it's not difficult to think of things that would be useful to do. For example, you can't, even today, compute weather forecasts at the scale where people normally live. You can't really compute a forecast for Leeds, which would be different from the forecast, say, in Wakefield or something like that. You might say, does anybody care? Well, you would care if you sort of, what about issues like human exposure to air pollution, which depends very much on the weather, and things like that. You really want to be able to make those predictions down to scales of kilometre, hundreds of meters. So there's quite a long way to go in some respects. So there's plenty to do here, but I've sort of put up, not to go through any detail. These are some of the big words, things that people these days work on. What do atmospheric scientists actually do? These are the sort of things that they do. Lots of big words. See, there's lots of aspects, and it's one thing you'll notice is there's a lot to do with the chemistry and composition of the atmosphere. Aerosols turn out to be incredibly important and have a huge impact on the Earth's climate. So that's what people are working on. So, bigger computers has got us to where we are now, along with all the other science. So, can we carry on this way? I thought it's quite nice to ask the question. We're at the 75th anniversary of the ENIAC experiment. So, what will it be like at the 100th anniversary? Where will we be by then? And we have a problem. It's getting harder and harder to run bigger computational models. And there's a number of reasons. One of them, some of you will be familiar with the concept of Moore's law. Moore's law is a rule about essentially the speed of computer processors. And for many, many years, decades, you could say that the speed doubled every 18 months. And that would give you a roadmap for how the speed of your computers would increase. And that stopped happening. Basic physics has got in the way. There's a limit to how small you can make things. and you can't make signals move around faster than the speed of light. So there was some weird fundamental physics that's got in the way. So Moore's law has stopped working, which means that you can only build faster computers by having more processors. So you can build that, make that as big as you want if you've enough money and power. But there's another problem then. The mathematical nature of weather models means that they don't like running on these very big computers with lots of processors. There are fundamental issues, and people try and work around it. A lot of work goes into that, but it's a massive problem. The other one is the cost of the computer. You're talking about now the largest supercomputers, hundreds of millions of pounds, and not only that, huge power consumption. And these days, the carbon cost of that is something that we have to worry about as well. So in a very real sense, just building bigger and bigger and bigger computers and bigger models, it's not going to work. So that's a bit bleak, isn't it? But then something else. So I like to think in terms of, in any scientific discipline, things come along that disrupt the trends and what everybody's doing. So what are disruptors for atmospheric science? And one thing that's happened in recent years is this climate change intensification. Things that we thought we had a roadmap for how climate change would evolve over the next decades. And suddenly the real Earth isn't cooperating and doing things that it's not supposed to. Like, the loss of Antarctic and Arctic sea ice is way ahead of what we thought it would be. The idea of these tipping points where there'll be sudden dramatic change. Basically, the Gulf Stream would suddenly turn on, and whilst the rest of the world would be very hot, we would be very cold. Things like that. There's this ever-increasing awareness and concern about pollution as well. But then the real big disruptor has been the sudden appearance of artificial intelligence and machine learning. And it's having a massive impact on weather forecasting models. I'll explain in the last few slides what it's doing, but essentially, these current weather forecast models we have, which are based on physics, huge amounts of physics, turned into computational science. In a very small number of years, those models could be dead. In other words, 75 years of advances since ENIAC could come to a complete end in a very small number of years, possibly in the next 3 years. And that's dramatic. So what are these models doing? Well, basically, it's about pattern recognition. It's machine learning. Some representation of the state of the atmosphere. Now, you put it into a thing called a neural network. You don't need to know what it is for these purposes. And you say, based on looking at lots of different patterns here, years worth of past data, take today's state of the atmosphere, what will it look like in 5 days' time, for example? And this has been done using old data to train this neural network, predicts future state of the atmosphere, and the results are extremely impressive. Not only that, but that computation can be done at vastly lower cost than these physics-based models. At least a factor of 10, but more like a factor of 100. Because the consequence of this is it's essentially a black box. You don't really understand how you got from here to here. You might not care, but you don't know. So that's sort of not so satisfying. In practice, you do it not by doing one big jump, but you train your neural network to predict, say, a 6-hour forecast or 3-hour forecast. And you do that repeatedly over and over and over again. Some caveats. The training and the initialization is still done with physics-based models. So they're not quite dead yet. I think it would be a very brave person who say that that problem wouldn't be overcome in a very small number of years. Some concern about what about really extreme events? Because they're extreme, they don't really appear very much in the training data. So how can you expect this neural network to predict an extreme event? The latest evidence is pretty good, actually. So here's an example. Some of you remember Storm Eowyn last year. So that this is the European Centre for Medium Range Weather Forecasts, and this is a 4-day forecast of Storm Eowyn. The colours are where the rain is. There's the UK. This is on Monday the 20th of January, and the forecast for Friday the 24th, and there's Storm Eowyn hitting the UK, and that's done with a machine learning model, not with a physics-based model. And the European Centre for Medium Range Weather Forecasts produced some statistics on the accuracy of their machine learning model and their traditional model. And actually, the AIFS is the artificial intelligence one, and it slightly beats the physics-based one. These are other models, and this is very telling. Here's some other models. Never mind what they're showing. Look at what they are. GraphCast from Google Mind, Pangu Weather from Farway, ForecastNet from NVIDIA. They're not weather forecasting agencies, they're big tech companies. So there's a very real possibility that the weather will be in the hands of the big tech companies before very long. I thought an amusement just at the end to do a comparison relevant to today. Sadly, the weather's incredibly boring. Don't tell me. I did consider finding a past case, but now I thought, no, let's stick to it. So this is the state of the atmosphere last Friday. And there's this essentially no rain over the UK virtually. There's rain because we've got an anticyclone over the UK, rain out in the Atlantic. Other things, you can see some rain, particularly over the coast of Norway. And there were some floods in Spain at the end of last week. And there's the rain, really heavy rain in Catalonia. So these are 3 different forecasts for midday today, starting from last Friday. This one's the traditional one, and we're still under the anticyclone. Well, that's definitely true. And these are 2 different versions of the AI-based forecast. I think what you can see, the 3 of them are all very, very similar. There are some differences. Don't know what that is. It looks like an ex-hurricane, but where that's come from, I don't know, because it's no longer there. That's a bit weird. Apart from that, this storms in Spain have moved further into the Mediterranean. That's true in all 3 models. Some slight differences, like some heavy rain on the coast of Norway that's hanging about. Western Norway isn't the place to be at the moment. So that's 3 5-day forecasts with the AI ones and the traditional ones, and they all look rather similar. So I just did this morning. This is what it's actually like, and it's like all of them. I mean, basically, from a practical point of view, all 3 forecasts are good. And you can see this. The storms have moved further into the Mediterranean. It is very unpleasant. You wouldn't want to be in Tromsø today. It's very unpleasant. But as far as the UK is concerned, the high pressure is keeping this is the rain out in the Atlantic. Yeah. So yeah, that's the AI does just as well as, if not better, than the physics-based model. So I thought this is just to sort of to sum up, and I'm not going to be able to answer all the questions about the future clearly, but I think asking the questions is the right one. So modern atmospheric science, we said, is 75 years old, but we're now in the midst of the second revolution. And suddenly it's possible to compute the weather without the physical understanding of the system, which has completely turned the whole subject upside down. What do we want to do? We'd like to be able to advance capabilities particularly to do things that predict down to the city dust in the street scale. And that's not changed. Whether the AI offers a way of doing that or not remains to be seen. And as somebody who, my job has been to run a research institute in atmospheric science, which is now 25 years old. So it's been around, but actually, we still think of ourselves as a young organisation. Actually, that's a third of the history of atmospheric science, so it's not that young. What will NCAS look like, and what will it achieve by this 100th anniversary over the next 25 years? And although that seems like a very long way away, it is relevant, I think, to ask questions like that. Not least because when you think about it, there are still people here in our institute who were here at the start. Not a huge number, but there are some. That's not me, actually. I wasn't there at the start. But there are a number of people who've been here right from the beginning. It's definitely true that there's some people here now who will be here on the 100th anniversary. So what are they going to spend their next 25 years doing? How will they develop their careers? And what is definitely true is what we decide now, as we're in the middle of this revolution, will have a very big influence over the direction, not just of this organisation, but of our subject over the coming years. So very interesting times, I think, and I can't say where it's going to go, but the idea that they've been sort of commonplace to talk about all the difficult problems in the subject have been solved. You know, nothing could be further from the truth now. We just really don't know where the future is. I'll leave it with that question. I'm very happy if people would like to ask questions. I'm going to try.
I suppose the measurement inputs must be maybe whatever is done with instrumentation.
Yes. It would be a topic for a different talk, but actually, yes, that's quite insightful because there's something we talk about now we call the observational deficit. For most of these 75 years, we were limited by the size of the computers, and by that I mean you could measure enough stuff, put into the model to be able to run the model and to check the results.
Time for making the forecast.
Yes. Well, you can run a forecast and you can pretty much check everything that comes out of the forecast at the end of it because you've got some new observations to do that. Somewhere about 10 or 15 years ago, computers had increased in speed, was some of the number of quality of the observations, but the observations hadn't increased as quickly. And basically, the computers had overtaken the models. And that means that today we can compute things that with no way of checking. So it's not the numerical weather forecast is based on not entirely on real observations, and we can predict things on scales where we can't then go out in the real world and say, was that correct or not? Because we don't have enough observation. And the difference between those is called observational deficit. So one of the things that really needs to be happening now, especially if we're going to do these sort of things like city scale forecasts, is to get new technologies to observe the atmosphere. It can't cost more, that's not acceptable, but the technologies that can gather a lot more data more easily, that's got to be one of the efforts over the next few decades.
Yeah, the more is known now about the atmosphere of different planets in the solar system. Has that enabled you to test the terrestrial atmospheric models? Or actually, I've both pursued going down different channels, modelling the planetary atmosphere.
Yes, it has, and that's a somewhat academic subject. But yes, it's there are people who are working on that, and these sorts of models are run for Mars and Venus and so on. Of course, we don't have as much data, but quite a lot of insight into these into building these models has come from looking at other planetary atmospheres. And of course, it helps to be able to test a model in a regime that's a long way from the one that you're familiar with. When I started my work, my PhD was with Raymond Hyde at the Met Office, and his lab in the Met Office was just as much about other planetary atmospheres as it was about the Earth. Because these days, financial constraints in the Met Office wouldn't dream of doing anything that wasn't to do with not just certainly the Earth, but probably it's a bit difficult. It's not to do with the UK. But in those days, real blue skies research went on in the lab.
When you gave the listing of why we've been able to tackle the problems better, I thought you were going to put up a surprise thing at the end. They realised that they were ignoring half the potential workforce in not recruiting brilliant women into insufficient numbers. Another facetious point is how long before the big tech companies have sufficiently taken on board what they're doing with this area of work, that they're able to compute the point at which big tech is going to ruin the climate so much that they're predicting the end of the Earth. It's not a serious question, but will they themselves realise what damage is being done in time to be part of the effort to counter it, rather than being in the big business of denialism?
Yeah, who knows? What they're responsible for is essentially the proliferation of computer power as well. What is it, taking on more than 10% of all the world's power these days and increasing all the time. Then them producing weather forecasts will be part of that. Of course, they're interested, not because they're interested in the weather, but the problem will become when they've squeezed out all of the forecasting agencies, so you will only be able to get a weather forecast by paying for adverts or whatever, that's the danger. All the time there's growing awareness of net zero considerations, the need to reduce power consumption, but they're pushing against that all the
They
time.
are.
So I can't say any more than you can about where this is going.
Well, your
This is
final
the modern
slide will, I'm afraid, be a vast field of dead puffins, I suppose.
Yeah, I can see very much how the big tech companies can take existing models and extrapolate them forward for a few days and say, yeah, the weather next week, next month will look like this. One of the areas I worked in was energy, And whether that precipitation you were showing up the Norwegian coast comes down as rain or as snow has a real effect on the river flow rates and therefore hydroelectric generation. Not just in the Nordics, but in the Alpine area as well.
Yes.
And I wondered whether there is still a place for modelling that longer term forwards for potential benefit for people who are taking long-term positions in the energy market, either as investors in hydro or planning for batteries, or simply speculating in the market.
There's no doubt that there's a big place for tailored or dedicated forecasts for particular applications. How that's going to fit in the future with this sort of big tech world, or whether it's past, the big energy company, they definitely have an interest in it. So whether forecasts would go that way, I just don't know. But there's definitely a case for very tailored weather forecasts for particular applications like the ones that we're describing. No doubt. And to some extent, that's happening. The people we could all get our free weather forecasts from the Met Office or Meteo Group or whatever. But companies are paying for weather services at the same time. So that's happening already. One of the big dangers, I think, is none of those forecasts produced by the tech companies can happen without the data representing the current state of the atmosphere, because they don't measure that. And who will invest in the observing networks to make that happen in the future? It's something else I didn't really talk about, but atmospheric science has, for very good reasons, been a pioneer in open data. These days, scientists talk about making all the data openly accessible, and this is a relatively new thing in some disciplines. But very soon, well, by 1950, the ENIAC experiments, it was realised that you couldn't do things like that unless everybody shared their data. And so one of the earliest things that the UN did was set up the World Meteorological Organization, and all the countries share their meteorological data. I sometimes blundered into things unknowingly because sort of in talking to scientists from other disciplines. And you just assume that everybody shares their data. And then suddenly they're offended. They think you're trying to steal their data. And because we've never worked like that. And we can't, because you can't do this subject unless everybody is open. But if the national organizations come to an end, then who's going to look after the sources of data? I don't know. So that would be a concern for the future.
Last question.
You touched on the three sources available for Met forecasts, BBC Weather App, Met Office app. Given the accuracy of short-term forecasts, why is there often such a variety of different forecasts on those two apps in the short term, and why do they change very rapidly over the course of a couple of days?
We're actually very involved in that. We haven't shouted because the BBC didn't want us to. When the BBC stopped getting their weather forecasts from the Met Office, they thought they might get a lot of criticism. So they decided to get somebody to provide an independent evaluation of their forecasts. And they came to us. So we had a contract for 7 years. We evaluate BBC forecasts, and behind the scenes, we don't discuss it with the Met Office. We compare it with the Met Office. And to be honest, they're incredibly similar. And for very good reasons. It's the biggest source of information for Meteo Group's forecast is the Met Office, actually, in spite of the fact that everybody thinks that they're independent. And most of the arguments come about with things like the BBC shows that dark grey cloud, and the Met Office shows a white cloud. People put their own interpretations on it. Underneath, the forecasts are incredibly similar. Most of the arguments are about how you communicate it to the public. And they've all got different ways of doing it. The BBC have recently decided that they are overly pessimistic and give people pessimistic view of the weather and they're trying to change it. But actually, it's very easy to at the level of weather charts to get a Met Office chart for tomorrow, Met Good, an American one, a European one. You can compare them all. They're all remarkably similar. Not surprisingly, because the technology is the same, and the data in particular is exactly the same because everybody shares the data.
Wonderful.
Stephen, thank you for a really interesting talk. I've got one question, one comment. Going back to Charlie, as you said, in 1950 he used one level.
Yes.
What height did they choose?
The
And was it terrain following, or was it 10-meter boundary layer?
didn't have a boundary layer, I don't think. It was 500 hectopascals, and there's an argument in the paper about whether it should be 500 or 600.
Right.
It's in the paper.
Okay.
It's inadequate, clearly, if you only have one level.
Yeah.
Then many of the real processes, like
Yeah.
bioclinic processes, atmospheric science, they're just not in there. So but it was more proof of concept. But yes, it's 500 hectopascals, which for those of you who don't know is sort of about halfway up in the atmosphere.
And my further comments, you showed us some forecasts for now, with high pressure being in charge. And I remember a comment from you many, many years ago. Never underestimate the ability for a high pressure to stick around. Do you still stand by that? And
Yes.
is AI going to change that in the future?
It's a good question
Your
whether
forecast
AI
of
is changing it. I don't know the answer to that. But although the forecasts of the breakdown of high pressure have got better, it's still underestimated. So if you see a forecast that says the high pressure is going to give way in 5 days' time, it's a pretty good bet that it will take 6 or 7 days in reality. Yeah. The interesting question, will AI do better? I honestly don't know the answer to that. In the example I gave, my view that it's not very objective. I thought the physics-based model probably high pressure was better than the AI, but that's just one case.
There you go, and I think we will go for
Rather more trivial. I expected Aristotle to come up in your forerunners, and he didn't.
He didn't. I could have done. And I could have given a whole talk about the early history of atmospheric science. There's probably people better qualified to do that than me. But yes, I started with Henry VIII really because I thought it was amusing what he said and how it sparked controversy all those years later. But no, because lots of things happened before. Things like understanding of things like rainbows and things that goes like 2000 years.
Just that you
Going back to that point, there's a very interesting connection between a very powerful man at the moment and Henry VIII. One had sorcery for forecasting of weather. The other has sorcery for not agreeing on climate change.
Yeah,
right, that was
lack of science.
Also like that.
Very.
Thank you very much, Stephen. Absolutely fascinating talk. I was reminded as I was listening an old joke sketch from I think around the fall, in which the newsreader says he's going to hand over to his colleague Marine to give the long range weather forecast for April, May, June, July, August, and September. which she does as changeable. I think Stephen, we are getting beyond that, and what you say, no, slowly, we are getting better and better at forecasting for longer periods, so possibly 6 months, which is a bit, but that's an absolutely fascinating tale of history and the potential futures in atmospheric science. So thank you very much indeed for your time and for answering all so many questions.